This session is composed of two presentations by two leading experts in theory and experiment, respectively. And first speaker is Professor Sankar from the University of Maryland, and he will talk about bilayer exotonic superfluids. Let's welcome the speaker.
Thank you, Hanki. Good morning, Allan, and good morning, everybody else also, but he's the one who matters. So I will talk about a subject which is associated with Allan MacDonald, at least in my mind, longer than all the topics you heard before, magnetism and magnetics, and in fact, longer than Flatlands. You know, the BM paper is like 2012 or 13 or 14. Allan has been working on bilayer exotonic superconductivity at least since 1994. And if you include quantum Hall, maybe slightly longer. So it's like 30 years. So he came to give a talk in Maryland last year. You can see the date. This is the abstract. He gave our regular seminar, exciton condensates through the years. And this talk had a profound effect on me. And that's what I'll talk about. Allan doesn't even know what effect it had on me. So in this talk, he actually talked about many things. So that's really a very inspiring, very detailed talk. Our seminars are supposed to be very, very technical. He went into technical details. And it's a work that not only involves one of my favorite senior theorists, Allan MacDonald, it also involves one of my favorite junior theorists, Feng-Cheng Wu. And this was just one figure from the talk. So never mind what all these systems are. It's a bilayer system. There are two layers, this red and green. They happen to be of TMD, and I think Kin-Phi may talk about it. But for our purpose, it's two layers. One layer has electron, one layer has holes. And then we are talking about this electron-hole system condensing into first excitons and then forming an exciton superfluid. This dream that started in, well, from Allan's talk, I learned the dream started in 1960 in a half-a-page paper. But I always associated with the former Soviet Union, Keldysh and so on in 65. And the electrons, the excitons then condense and create a superfluid. And there's a phase diagram. Phase diagram typically always has separation between the two layers. That's one dimensionless unit. And chemical potential, think of it as density, electron density. These are the only two variables at zero temperature, electron density. And this also has band structure complications, which I'm not going to worry about. And then these are the superfluid phase. Ignore this white part where, because of band structure reason, nothing interesting happens. There are not even any excitons. For my purpose, it's not very important. I'm interested in this part. This is, they did a calculation and they found superfluidity. These are two different kinds of superfluidity. Everything is fine. Everything, I have no problem with everything. I totally agree. But then this figure caption has this sentence. For NAB square larger than 0.1, the exciton condensate ground state, which is there, NAB square larger than West somewhere for very high density, is expected to be superseded by an electron hole plasma state. This totally threw me off kilter. And I just could not, I could not go on. I could not pay attention. Why? Leon Cooper told us in 1954 that you have attraction in the Fermi surface. It forms a condensate. That is it. That is the electron hole plasma, okay, at zero temperature. These are zero temperature phase diagrams. I gave Allan trouble. He knows me long enough to know how to avoid me. He avoided. And, he avoided in his own inimicable way, okay, which is if you know him, you know what I'm saying, okay? But in any case, this really not only traumatized me, traumatized a lot of people. Allan, I'm not exaggerating anything. You can ask these people. This talk in April 23, because I said there is no electron hole plasma phase. There cannot be a zero temperature electron hole plasma phase here, okay? That's impossible. Finite temperature, sure. The TC may be 10 to the minus 100 Kelvin. I don't care. There is a zero temperature phase. And I then traumatized 8 young theorists, all of whom I paid salary or at some time or something in 4 different institutions, leading to 6 different papers during the last 12 months. And now I'll traumatize Allan by telling the story of these 6 papers. So, and the point is that I also bothered a lot of people. I bothered Jim Eisenstein. I bothered Philip Kim. I bothered Harf Farty, Kun Yang, Kin-Phi Mek, Feng-Cheng. I didn't bother Allan because he started the whole thing. I also bothered poor Bert, who wrote a like 6-page response to me, and Corey Dean, because I'll show you why I bothered many of these people. So this is the story. But if I get to the story, let me just tell you that, well, Allan visited, so this is a dinner after that, and this is not any kind of crazy or funny picture like Thomas showed. We both look very happy. We don't look drunk, but you are actually drunk. There's a nice bottle of Barbaresco Malbec. The restaurant we went to did not have big, expensive left bank, but it had decent Barbaresco Malbec, so we're very happy, okay? This is Bombay Club. You're looking good, Allan, in this picture. Okay. Now I met Allan through Steve Garvin, who I hope is in the audience there. I remember Steve telling me, I think it's 1983 summer. I don't remember because I don't have a CV anymore, so I could not look up anything. But I think I distinctly recall Steve was at NIST. So we used to talk all the time in the context of quantum Hall effect. And he told me there is this absolutely wonderful physicist, Allan MacDonald, whom I would like very much because he worries about electron gas and so on. And then Allan invited me to a conference he was running. This may be in 1984, Allan, I'm not quite sure. And I went to Ottawa, and there's a very good conference. I'm sure Steve definitely was there. Allan was there. So that's how long I know Allan, since 1983. 84, okay, see, 84. I told you I have a question mark. I wasn't sure, okay? And so I know Allan for 40 years now, which is longer than 50% of the people in this room have been around, right? Or more than 50%, okay? And certainly longer than any of the prior speakers, okay? And only Steve Garvin in this room certainly knew Allan longer, and maybe there are a couple of others I do not know. And then in I have many things with Allan, but I cannot talk about all of them. Then in 1992, we were all in Australia, thanks to Bob Clark. Some of you may remember who he is, quite a character. And when I say we, I really mean we. Allan, Susan, their children, and Janet and I. This was wonderful. We were there for a month because Bob Clark was founding the high magnetic field facility of Australia. And he somehow thought that Allan and I could help him. I do not quite know what he was thinking. I don't think we helped him, but we started that thing. Remember, we switched the power on. And Allan and I apparently also, I found all these things by Googling. Allan and I apparently also co-edited a lot of journals, must be thanks to our late friend, Aaron Pingzuk. We have 3-4 solid-state communication issues that we co-edited with others, We ran ITP and Aspen program together, and we visited each other many times. So we go back a very long way. So I'm delighted to be here. Although I know these things are embarrassing you because I know you, but there's a lot of physics here too. So, but probably my strongest connection to Allan is through intermediaries. Allan has been relentless in sending me his students as postdocs. I counted 7 of them. And 3 of them I'm actively interacting with right now. Mingxi and Jihang Zhu are actually in Maryland now. I think they're here right now. They're with me now. Feng Cheng is back in Wuhan, but we write lots of papers together. And Enrique and Honky are here. And I was going to make a comment. I was going to ask Allan that, do you know the whereabouts of Lian and Junhu? And they showed up. They came to me and said, do you remember us? Just 5 minutes ago. They took my thunder away. I was going to ask, where are you? And then they should have stood up. So it's wonderful. And Allan, please keep on sending your students, but only the good ones, please, okay? We also wrote some papers. Somewhat to my surprise, I found we wrote only 3 papers together. I would have expected more, but this is all I could find. And this one is quite well known with Kuhn. We're both at KITP on a graphene program, and we have some other papers on various quantum phase transitions. So I'm going to stop here, my reminiscence with Allan, and get to the main physics. So I'm going to talk about bilayer exciton condensation. And these are the 8 people that I talked about. Srijit is in Pune. Jihang Eating2 is a student. Jihang is a postdoc who was Allan's student. She's in the audience. Tessa is a postdoc in KITP. And Tessa actually is a quantum spin liquid expert. But after her quantum spin liquid work, she wanted to do more things with me. I asked her if she has ever done Hartree-Fock. She said, no. I said, okay, you cannot be a theoretical physicist without doing Hartree-Fock. Allan MacDonald would not approve. So you must do Hartree-Fock. So Tessa learned Hartree-Fock and did it. Sage Davis was a postdoc in Maryland. Jaideep Sai is my colleague in YVU, who was a student with me at Harvard, Yangzi Chow. All of them actually wrote papers. And what I'm going to tell you is that electron hole 2D bilayer, I'm talking only B is equal to 0. Jim Eisenstein, who's giving the next talk, will talk about finite field, where many interesting things happen. So this was predicted in 1975 by Yuri Lozovic, who's recently passed away, actually, in Russia. But I'm also going to talk about electron-electron and electron-hole-hole, because exactly the same physics happen in both systems. You know, there are no holes. Holes are just absence of electrons. Electron-electron interaction in solid is always repulsive. So when you say electron-hole attraction, this is a figment of our imagination through band structure. So anything that happens for electron-hole should happen for electron-electron also. And I'm going to talk about that. There is no interlayer tunneling. So this is a spontaneous interlayer coherent phase. And I'm going to show it happens for both electron-hole, which is well known, superfluidity, and electron-electron. This is just breaking of U1 layer symmetry. For electron-hole, it's better to think of it as superfluidity. For electron-electron, it's better to think of it as a pseudo-spin XY ferromagnetism. But they're the same universality class. And for quantum Hall effect, they're exactly the same. The two pictures map into each other because of an exact electron-hole symmetry. So in the quantum Hall, originally, when Steve, Allan, they were working on it, it was mostly talked in terms of pseudo-spin XY ferromagnetism. Later on, even for quantum Hall system, the language changed to interlayer superfluidity. They're the same for quantum Hall, but not for electron hole zero field. I'm going to show you results. Mean field, 8 smart people working on it, 6 papers. We did every technique that theoretical physicists know. Mean field, Elias-Berg, bosonization, RPA, RG, everything. Because I was obsessed that I'm going to show there is no electron hole plasma phase, okay? And I'm going to talk about only zero field situation. I will not get a chance to talk about this 1D problem done by Yangzi Chow and in YVU, where we do RG bosonization and exact diagonalization. Results are consistent. These are the papers. No need to read all of them, but I just wanted to prove that there are 6 papers, all written in last 10 months, okay? I'll mostly talk about the things in green. But the story began for me at least a long time ago, and there'll be some familiar names here. So this is the paper where he showed that electron system will have this U1 breaking instability also, because of the Heisenberg system, not a Ising system. And then there was a KITP meeting, and my only paper with Matthew Fisher and Steve Garvin was written here. Steve and Matthew probably remember, right? It was like a one-day discussion and then some calculations, and somehow Sarma Mitra was not as tough in those days. It was a PRL, okay? He has become very tough now, okay? But in those days, he was not that tough. So anyway, so those were good old days when we discussed things on that. So let me show you an early paper on graphene by Allan MacDonald. Very, very good paper, and Rafi is on it also. Rafi is in the audience. Of course, Bischiser and MacDonald are very well known for other work now, but they did many things that I like. So they predicted that in graphene bilayer, you have room temperature superfluidity because the stiffness is large enough that you don't need to go to millikelvin. And they did a calculation, Hartree-Fock. Here is the calculation where they calculated TC, and you can see that TC can be very, very large in graphene. It's absolutely correct calculation. In gallium arsenide, the numbers are actually lower. This is a mean field theory. Screening is neglected. True mean field, Hartree-Fock. Neglect of correlation, neglect of disorder. And these first 3 items actually do not apply to quantum Hall system, but disorder applies there also, but disorder is low. So the question now is what would happen if you include these effects? So Enrico Rossi, who was Allan's student and then a postdoc at Maryland, we were influenced by this work and we were wondering why it is not seen. And we did some calculation including disorder, and we found disorder, particularly charge impurity disorder, which is very important for graphene, will play a very important role. This delta mu is a measure of charge impurity disorder. And as you can see, when delta mu increases, it's nanovolt, it's still very small. TC is suppressed very, very strongly, okay? So you have to have very, very pure system to see this is the same thing shown in a different way, but basically concluded that it will be very difficult to see it in graphene, and B is equal to 0, excitonic superfluidity in bilayer graphene has not been seen. And now, the point is that This is different from not seeing superconductivity in copper. You know, copper doesn't go superconducting even at 0 temperature, because you have this mu star that Macmillan told us about. This is the formula for superconducting transition temperature in BCS theory, lambda star. Lambda star is electron-phonon coupling minus electron-electron coupling. And so that is repulsion. But here, everything is repulsion. So here, the attraction, so it's the reason it's not seen is disorder screening TC is very low. If we could go to 0 temperature, 2 layers of graphene will definitely be superfluid if you have electrons on hole doped. Okay, but TC just happens to be very low, and this problem may be resolved someday. Okay. Actually, I wrote a paper even before that I think Yogesh Jagalkar was either Allan's student or postdoc. Okay, so then he was a postdoc at Los Alamos, and I was visiting. Sasha Balatsky was there. We started talking, and the question came up that if you have electron hole bilayer, they form exciton in some regime. Maybe those excitons will go superfluid in some situation. We then cooked up a phase diagram, and we showed, we basically hypothesized that the same phase diagram drawn differently, separation D is in this direction and inverse density in this direction. We said that, well, look, when you have very strong exciton first, so almost like bosons, you will have a Wigner supersolid. You will first form because the RS is so large, density is so small that the system will form a Wigner crystal, and then excitons will condense in that Wigner crystal phase. So supersolid is a phase that is similar to what Thomas was talking about. It breaks both U1 symmetry and translational symmetry. So you have RS very large, so you have a Wigner system which has broken translational symmetry spontaneously, and then you break U1 symmetry, the bilayer U1 symmetry, so you'll have this, and there are claims this has been seen, recent claim. But notice here, I make the same mistake that Allan is talking about, because this phase diagram was done by Jagalkar. Everybody says this electron hole plasma, when the density is very high. There are variational Monte Carlo calculations showing this. Variational Monte Carlo calculation is very nice. You can show whatever you want. Just choose your wave function appropriately, okay? Anything, okay? I mean, you could have shown this is a chiral superconductor by choosing. In any case, so this is a very common conceptual mistake. So I made it also, so Allan is safe, okay? Recently, Corey Dean and Leo Lee, I had a rumor Leo Lee is coming here, is that correct? Okay. They wrote a very nice paper where they claim to have seen this supersolid phase. Very nice paper, but I'm not going to talk about that because it really will take me very far. All right, so this is the paper of Philip. I don't know if Philip is in the audience, Philip and Corey. And this paper, main part that I'm interested in, this is in finite magnetic field. They saw in quantum Hall effect this exciton superconductivity, first seen by Jim Eisenstein in the 90s. This is the phase diagram, a very complicated phase diagram. We have exciton gas, T is in this direction. You have B, C to BCS superfluid. This is fine. But look what happens. Bert Holper is the co-author here. Bert never makes any mistakes. But look at electron hole plasma, it keeps on going. So I wrote to Bert. I said, Bert, this figure is wrong. Because look, it's going all the way to T is equal to 0. Bert got totally rattled and sent me like a 5-page long thing. But then I actually saved him by saying, well, your x-axis, maybe your x-axis here is a 10 to the minus 10 Kelvin. Then it's okay. TC is, it just, as long as it's not 0, it's okay. So nobody has, since you only see electron hole plasma, you're always doing finite temperature experiments, right? So you are not seeing the condensate. You see electron hole plasma because of finite temperature, right? So you just assume it goes to 0 temperature. It does not, okay? 8 young people showed that, by working very hard. All right, so that's all background. Let me now show you the theory, okay? I already gave you the punchline. So first, Hamiltonian. So the Hamiltonian is very simple. You have kinetic energy of the 2 layers. You have the interaction energy, and you have this is the energy, okay? And we are doing BCS type theory, so you solve this BCS equation self-consistently. This is the Hartree-Fock theory or mean field theory. So mean field BCS theory always gives you superfluity at t is equal to 0 because of Cooper pairing arising from electron hole excited matter. You cannot avoid it. Only issue is that this is going to be very low when density is very high. This is nothing other than BEC to BCS crossover. When the excitons are very tightly bound, they are like atoms, that's BEC. And when the density is very low, electrons and holes are very far, that's like BCS. BEC phase TC is very low. But there is no critical point there is no quantum critical point here. Okay? This is just a classical thermal phase transition at finite TC. And our work showed that. We did finite temperature calculation. Again, I'm not going to go through the details. This is not very relevant. But the important thing is that you have a TC. TC drops very fast as a function of D. These are all different densities. We plot in a variety of different ways. And then we go on and introduce screening later on, and it goes. But this doesn't answer the whole question. If you know anything about superconductivity, the gold standard of superconductivity is Eliashberg theory. To my total amazement, this is something Allan left for me. Or maybe he did it, I didn't know. I don't know why, but it's a very, very hard calculation. So we did the full Eliashberg theory for this problem. We did an RG theory, but I wasn't satisfied with that because RG will always give you a phase. I wanted to do the actual TC, how low the TC is. So the full Eliashberg theory, if you don't know what Eliashberg theory is, I cannot explain that here. Basically, what you're doing is you are treating the problem completely on the same footing. Electron-electron interaction, self-energy, electron-hole attraction, repulsion, everything is put on the same footing. You are keeping all the self-energies, doing the full calculation at the leading order approximation. So you have screening, you have renormalization. You are solving a whole bunch of coupled integral equations self-consistently. Not an easy thing to do, but I had this feeling it is doable. Okay, I have no clue how to do it, but young people can do it because you have to solve this set of equations self-consistently. And Srijit, who was visiting us on a sabbatical, his background is quantum Hall effect. That means he's fearless in doing very hard calculations. So he carried out the full Eliashberg theory calculation. And let me just give you the bottom line of what we found. What we found was that when you do full Eliashberg theory, when you do just mean field with no screening, you get a very large TC, as you'd expect, okay? Very large TC. Then you do static screening, the TC drops completely, it becomes unobservably low. So static screening is very strong. This was already known. Okay, somebody pointed it out after Allan's paper. I think Efetov pointed it out. That's absolutely true. This is true always. That static screening overestimates screening. But when you do full Eliashberg theory, it comes back up. It's in between. I mean, this result is not surprising at all. But you actually showed this is what happens. This is not just figure drawn by hand. This is actually microscopically calculating full Eliashberg theory for this problem, which I think Srijit was the first person to do it. And I'm actually very fond of this calculation. Here is the unscreened mean field. You see that for various density, what's happening. Here is static screening, complicated things happen, but the scale goes down enormously. And then this is static screening, the scale goes down. Then I already showed you, I think, the dynamic screening results. So for dynamic screening, the result is in between. So there is some hope one may be able to see it. So, but what we found is that you always have a condensate. It's just a BEC-BCS crossover. At 0 temperature, there is no phase transition. Okay? You have a BEC at very high density. You have a BCS at very low density. TC could be very, very low. That's a different thing. Now, of course, at finite temperature, we have the finite temperature phase diagram also. The TC could be very low, so it would look like heavy electrohole plasma. Okay. Now let me spend the rest of the talk, which is maybe 7-8 minutes more, to talk about the electron-electron system. That also has a long history. Lian Zheng is in the audience. We wrote a paper in 1997, actually 1996. Idea is very simple. You have 2 layers. Each layer is filled with electrons. Electrons have 2 spins. So what are the possible phases that you can have as you lower density? Well, the electrons could become ferromagnet, like we heard in the talks in the morning session. So then electrons will either polarized spin up or spin down in both layers. This is the block ferromagnetic transition, right? But if you ignore spin, then another transition is possible. You can think of these layers as a pseudo-spin, right? They don't obey SU2 symmetry, but they obey U1 symmetry. So you ignore spin for a second. If you ignore spin, what is going to happen? Well, it will become a layer magnet. So you saw, then all the spin up in layer means all the electrons going into one layer. That's layer index, all the pseudo spin is up. And that's what people thought. And there are even experimental papers claiming this has been seen. The spontaneous depopulation of a layer. There is no tunneling. Remember, tunneling is zero. It's just that when a ferromagnet happens, you don't apply a magnetic field, right? All the spin spontaneously polarize in some direction. It's exactly the same thing here. And there is an experimental claims it has been seen. But this, I did not believe this. This is an Ising system. This is not an Ising system. This is a Heisenberg system. There is another phase we know, which is a phase which is kind of a linear combination of these two. So we showed in this paper that that's what happens, that you have the purely paramagnetic phase where all the spins are unpolarized and the layers are unpolarized. Then you have S1 phase, which is layers are spin polarized, but both layers are occupied. And then you get a phase which is historical name SP, spin polarized symmetric, where what happens is that both layers, although there was no tunneling at the non-interacting Hamiltonian, the system behaves as if there is spontaneous interlayer coherence. Okay, and you can describe it as in this layer pseudospin language, it's an XY ferromagnet. Okay, and we showed that always has lower energy. It's a theorem that always has lower energy than the pure ferromagnet, at least in the Hartree-Fock level. Okay, so what is happening is that originally you had no single particle tunneling, but the system creates a linear combination of left and right spontaneously as if there is tunneling. Okay, tunneling is spontaneously created. And there are Goldstone modes associated with, and the Goldstone mode is what Matthew, Adi Stern, and Steve Garvin and I calculated. I got back to this problem recently when Jihang Zhu came to Maryland. I thought that we never really completed this work. We should get the TC. We should get what happens when the layers are imbalanced. We should see whether there can be pseudo spin density wave state. There are many, many, many questions that in electron gas problems have been studied in great details. Okay, like Overhauser told us in 1962 that within Hartree-Fock theory, metals are unstable. You get spin density wave, you get charge density wave. What about those phases for this layer problem? So Jihang Zhu, and with some help from Tessa Kookmaier in the second paper, did an amazing job. These are the papers. And this is just too much physics. I don't know to give you all the results. There are too many variables like layers, density, temperature, fractional density. But all the pictures, these are all 30-page paper, all the details are there. All kinds of symmetry breaking are possible, and they all happen. We did not do Eliasberg theory here, but one thing we know that anything you get in Hartree-Fock happens in nature, maybe at somewhat higher coupling constant. So I'm convinced all these things exist. So yes, this XY ferromagnet exists, and yes, there are all these density waves. They are also, pseudo spin, and we compared electron hole bilayer, and as you'd expect, the TC typically is higher in the electron hole bilayer, but the same physics applies. Although here it's an XY ferromagnet, here it's a U1 symmetry breaking superfluid, but they're of course in the same universality class we know. So it's same physics. It's just the description is very different in physical terms. So the story is basically complete. Okay, and you can have FFLO phase here. I mean, these papers are very rich. You can have FFLO phase when the two layers have different density. That was worked out. It's very satisfying. It's like a book. These papers together is like a book, And the only thing is that writing papers, struggling with referees was not very is not enjoyable. But I really like it, and it's all Allan's fault that he came and gave a talk, and nothing like listening to a talk to sharpen the questions you have. So Allan's talk was so crystal clear that all these questions came up, and I think we answered it. And I think I'm going to stop. I can go on all day on this. I'm very enthusiastic about it. With this figure, which shows you Jihang's cartoon of these phases, I'm going to stop here. Allan, congratulations for so many years of physics and for inspiring all of us. and sending me all your students and deferring to me in restaurants when it comes to wine. Okay, so thank you.
We have time for questions and comments.
Can I ask a question? All right, thank you. So Sankar, the transition between this condensate phase and electron hole droplet, would it be a continuous transition or first order transition?
It's first order.
It's first order.
Yeah.
So can you actually find the first order transition within the formalism that you used? It's not an instability.
No.
Right. So
but meaning we can, but you have to add something to it. Okay,
right.
Like Maxwell's drawing or something. So we can just compare energy and say it's first order, which is why I'm saying it's first order. Okay?
Right, exactly. So, but did you check for chemical potentials crossing, or what then is the statement that
the results are all in the numeric? But at some point we got exhausted and worked more on the pseudospin density wave and so on and so forth, which we thought would attract. But this is something we can do. I mean, maybe we should do it. Jihang is here. Okay, Jihang, you are working only on 5 projects. This is your 6th project. Okay, so it's done. Trust me, it's done. She's very good. No, this is a very good question. We should do it. I mean, honestly, because it may give the experimentalist a clue. Oh, by the way, I forgot to mention there's a paper from Harvard. There are always papers from Harvard. Okay, there's a paper from Harvard claiming they have seen this coherent phase. It's very recent paper claiming. I didn't show it because I did not study the paper carefully.
All right, thank you.